Good morning. I welcome you all to this session of fluid mechanics. Now, if you recall, last time we are discussing about the buoyancy, phenomena of buoyancy. What is that? Again, just if we recall it, if a solid body is either partially immersed or fully immersed in a fluid, the net horizontal force in any direction because of the pressure exerted by the fluid on the surface of the body is zero. But the body experiences a net vertical force in the upward direction. That means the resultant of the pressure forces on the surface of the body, that is immersed body, either fully or partially, is in the vertical direction, upward vertical direction, and its magnitude is equal to the weight of the displaced volume of the fluid. What is the displaced volume? That is the volume, immersed volume, that is the volume of the solid immersed in the fluid. In case of a fully immersed body, that is submerged body, then the displaced volume is the volume of the whole body itself. So, weight of that volume of the fluid is the magnitude of the upward hydrostatic pressure force, which is known as buoyant force, and this phenomena is known as buoyancy. Now, then afterwards we recognized that for an equilibrium condition of the body, first let us consider the submerged body, but it is valid for both submerged and partially immersed body, that for equilibrium the primary condition is that the weight of the body should balance the buoyancy force, upward buoyancy force, by magnitude and also by the line of action. That means weight of the body should be equal to that of the buoyant force, and these two forces must be collinear for equilibrium of the body, either in floating condition, that is partially immersed condition, or fully immersed or submerged condition. Now the question comes that probably you have already read earlier in mechanics, that an equilibrium is of three types. One is stable equilibrium, another is unstable equilibrium, another is neutral equilibrium. What is meant by stable equilibrium in general is that if a body is in equilibrium under several forces at a particular instant, now if you disturb the body to just depart from its initial equilibrium position, whether the body is able to come back to its initial position or not. If the body is able to come back to its initial position, that means force system acting on the body is such that it makes it possible to restore its initial equilibrium position, then this type of equilibrium is known as stable equilibrium. That means equilibrium is stable. It is a question of reproduction. Just the body is capable of reproducing its initial equilibrium position under any small perturbation. To distort or to allow the body to depart from this initial position, it will again come back to its initial position. Now, unstable equilibrium is such that if the body is in equilibrium under several forces at a particular position, if you disturb the body to depart from its initial equilibrium position, the force system is such that it does not allow the body to come back to its initial position. It goes on departing from its initial equilibrium position, and in fact the entire equilibrium condition of the body is destroyed. This is known as unstable equilibrium. So, equilibrium is there at a particular position at a particular instant, but this is unstable equilibrium. Another type of equilibrium is a neutral equilibrium, which means that if you give a disturbance to the body, then the body will neither come back to its original position, nor it will go on departing further and destroy its equilibrium condition. Neither of these two, but body will remain again in the equilibrium condition at that point. That is sleeping person. That a sleeping person, if you take him from one position to another position, he will be keeping there itself in equilibrium, like that is neutral equilibrium. A very simple example, probably you have read at your school level, that if you place a marble on a hill or on a table of convex shape, if you place it, it may be in equilibrium, that the weight may be balanced by the reaction force if there is a contact surface, but if you slightly perturb it, that means if you slightly push it, this will go down because of the convexity of the surface. That means this is in unstable equilibrium. Similarly, if you place a body on a surface which is concave inward, and you place a body, it is in equilibrium, the weight of the body is equal to the reaction force. If you give a displacement, then it will again come back to its original position because of the concavity of the surface. That means this is an example of stable equilibrium. And neutral equilibrium example is very simple. On a flat table, flat table, if you place a body, for example, this is in neutral equilibrium. If you place it here, it is in equilibrium. If you place it here, if you just don't consider the rolling of it in the, so it is in equilibrium. So that means this is a concept of neutral equilibrium. Now in case of buoyancy, this perturbation to study whether the body is in neutral, stable or unstable equilibrium depends upon its perturbation in angular direction. That means if we just displace the body or give a small rotation, then we see its stability. That is why sometimes this stable equilibrium, unstable equilibrium, neutral equilibrium is coupled or is referred to as angular stability of the body. So body is linearly stable when weight and buoyancy force are equal in magnitude and are collinear. But whether a small angular displacement allows the body to come back to its original position or not is referred to as angular stability, or in general to stable, unstable and neutral equilibrium. So let us now see that let this be the free surface of the liquid. Now let us consider first submerged bodies. First consider submerged bodies. Well, first consider submerged bodies. Now what is the condition? Let us see a body like this. Let us see a body like this. Let us consider. Now you see the center of gravity and center of buoyancy should be in this line. Now there may be three options regarding the point of application of center of gravity and center of buoyancy. One option is that center of gravity may be, this is center of buoyancy. Center of gravity may be below the center of buoyancy. Another option is that center of gravity may be coinciding with the center of buoyancy. Another option is that center of gravity will be above the center of buoyancy. This depends upon the relative distribution of mass over the volume. When gravity is below the center of buoyancy, it is bottom heavy. When gravity is above the center of buoyancy, it is top heavy, and when the mass is distributed uniformly throughout the volume, these two coincide. Now let us first consider when the center of gravity is below the center of buoyancy. What happened? Through center of buoyancy, the buoyancy force Fb acts. Through center of gravity, the weight W acts, and they are collinear and equal. Always W is equal to Fb. So this is in equilibrium. Let us give a small tilt or angular heel of this body in this direction towards the right. Let me draw this figure. Now in this tilted condition, let us see the body. Let us see the body. Now this is this axis of symmetry or the original vertical axis, whatever you can tell. Now the center of gravity with respect to the body is unchanged. This is of course not true for all cases. I will explain afterwards. In certain cases, if some solid part of the body moves, for example, when a ship moves in a river, some of the cargoes within the ship moves from one part to other part. So therefore the mass may change, but if we consider a tight solid body, the center of gravity remains unchanged and the weight acts vertically with center of gravity. Now the center of buoyancy also remain unchanged in this case. This is because what? The center of buoyancy is also the center of the volume, and when in submerged bodies the entire volume is submerged. So here also entire volume is submerged. In both the conditions the bodies are submerged. So center of buoyancy also will not change, through which the buoyancy forces acts. Now in this case you see these two parallel forces creates a moment or a couple, which is, now this is the direction of tilt. So a couple is generated in the opposite direction, whose magnitude is W or Fb, whatever you call, both the forces are equal, times this distance, times this distance. If you consider this distance as x, W into x. That means in simple we can tell in these circumstances, this Fb and W creates a couple which is opposite to the direction of the tilt, and this couple is known as restoring couple. So this couple is restoring couple. That means which restore its position. That means this couple helps the body to come to its equilibrium position. Now if you give a tilt or heel in the left direction, you will see again the body a buoyancy force and the gravity force makes a couple in the opposite direction to the angular heel of the body. That means it always creates a restoring couple and helps the body to come into equilibrium. So when G is below B, we see the equilibrium is stable equilibrium. So this is stable equilibrium, stable equilibrium, stable equilibrium. Now let us consider a case when G is above B. That means the distribution of the force is like this. Distribution of the force, distribution of the mass over the volume is such, that means it is top heavy. That means G is, this is G, and let B is below G. That means through G the weight of the body acts and through B the buoyancy force acts. But it is in equilibrium, that means W is FB. This is valid. Now if you give a tilt, it is very simple, school level thing. So if you give a tilt in the same direction, that means rightwise, towards the right, if you give a tilt, this is the original vertical axis. Here again, in this condition, the gravity remains the same, the center of gravity and also the center of buoyancy. Now you see these two forces, W and FB, they create a moment which is in the same direction to that of the angular tilt. That means when you give a tilt in this case, the two forces FB and W whose collinearity is destroyed, they create a moment in the same direction or couple in the same direction and helps the body to tilt further. So therefore the body departs from its original position further and further and equilibrium is never attained. This case it is known as unstable equilibrium, unstable equilibrium, and this couple under this condition the value of this moment, that means W or FB times this perpendicular distance, is known as overturning or destroying couple. Sometimes we call overturning, this is the terminology in mechanics, or destroying couple, the couple which destroys the equilibrium. Therefore we see now in this case also, if you give a heel in the left direction, you can again examine that the couple created by the destruction of the collinearity between FB and W, the couple created by these two forces again will be in the same direction of the angular tilt and creates a overturning and destroying couple and makes the equilibrium as unstable equilibrium. Okay. Now the last possibility is the possibility that G and B coincides. That means this is the case where the mass of the liquid is distributed, this is G, uniformly over the entire volume. That means the weight acts to the center of gravity and the same point is the center of buoyancy, that is AB. That means the mass is uniformly distributed over the entire volume. In this case it is just like a neutral equilibrium, as I have told earlier. That means if you displace it, if you displace this under the displaced condition, that means if you give angular heel in this direction, GB both will be same. So this will be the new vertical lines and they will be again collinear. This is W and this is FB. So it will be again collinear. That means under any angular location and at any angular displacement at this position, it will be in equilibrium. It will neither go further in this direction or will come back in this direction. This is known as neutral equilibrium. This is known as neutral equilibrium. So therefore, what we conclude is that when a body is totally submerged, the condition for stable equilibrium, that means angular stability, then if the body is given a slight angular heel in either direction, whether it will come back or not, depends upon the fact that when G, the center of gravity, is below the center of buoyancy, the body is body has this angular stability, means stable equilibrium. If the center of gravity is above the center of buoyancy, the body is in unstable equilibrium. That means it doesn't have the angular stability. If you give a small angular heel in either direction or part of the body, it will go on departing from its original equilibrium condition and the entire equilibrium will be destroyed. This is the case of unstable equilibrium when the center of gravity is above the center of buoyancy and the Last case is when center of gravity and center of buoyancy coincides. That is for a special case when the distribution of mass is uniform throughout the volume of the body. In that case, the body is in neutral equilibrium. That means if you give any position with any angular position at any inclination, at any configuration, if you submerge the body, body will be in equilibrium at that particular configuration itself. That is the concept of neutral equilibrium. Now we will discuss the same thing under floating condition, but there is a difference. First of all, you must know that why separately we are discussing the submerged and floating bodies. What is the key point of difference between a submerged and the floating body? First difference is that, as it tells very simple, literally, that a floating body means a part of the body is submerged, not the entire volume of the body is submerged in the fluid. Therefore, the buoyancy force will be equal to the weight of the displaced volume of the fluid, that means weight of that volume of the fluid which corresponds to the immersed volume of the solid. That is number one. Number two is that obviously under equilibrium condition of a floating body, the weight of the body must balance the buoyancy force, and next is that they should be collinear, and buoyancy force equal to the weight of the displaced volume. Therefore, floating body requirement is that the density of the body has to be lower than the density of the fluid, so that the weight of the displaced volume of the fluid, which is the immersed volume, partially immersed, that means not the total volume of the fluid, must be equal to the weight of the fluid. This is very simple, you have read at school level. Now what happens when you give an angular heel for this floating body? What is most important is that here, though the center of gravity may remain unchanged if there is no movement of mass within the solid body, but center of buoyancy is obviously changing. This is because though the total displaced volume remains same to make it equilibrium and to be equal to its weight, but some portion is getting more immersed and some portion is getting out of the water level depending upon the direction of the heel. So therefore, the center of buoyancy, the distribution of the immersed volume changes, though the total immersed volume remains same. So that center of buoyancy moves, it doesn't become same as the earlier one which we saw in case of submerged body. That is the key difference, so that it comes separately for investigation of the angular stability in case of a floating bodies. Okay, with that let us see that what happens in case of a floating body. Okay, good. Now let us consider this is the free surface, and let us consider the floating body, a typical cross section of a ship. Let us consider a floating body like this. This is the axis of symmetry, a symmetrical body like this. Now let us consider a floating body. This is the part which is immersed in the fluid and this is outside the fluid. Let us consider this is the initial position, and here we will see one interesting thing. Now first of all, if gravity is below this center of buoyancy, center of gravity, it is always been stable equilibrium. That you can see by yourself. I am not going to that. Let us consider the gravity is above its center of buoyancy. Now we have seen in case of submerged bodies, they immediately obviously tell whenever the gravity is above the center of buoyancy, then obviously it is unstable equilibrium. But in this case it may not be so. Then angular stability may not always be destroyed if the center of gravity is always above B. You cannot tell that. Now center of buoyancy is the center of this volume. Okay, and we consider the center of gravity is above B. One thing is true, that the weight and the buoyancy force, that is always true, they balances each other. W is equal to A. Now in this case what happens, now what I have told just now, you see that if you give a small tilt in this direction, and let me draw the figure like this. Now let, in the displaced position, this is the old line of symmetry, or the line which contain the center of gravity and the center, old vertical line containing the center of gravity and old center of buoyancy B. Now it is obvious that if I retract or retrace this line, let this line be this line. So therefore we see that this portion of the body hatched portion has gone out of the free surface which was earlier there underneath the free surface, and this portion of the body which was above the free surface has gone down below the free surface. That means that if we give a tilt here, more of the volume in this portion will go under the free surface and some volume in this portion will automatically come up. So therefore we see the distribution of the immersed volume changes. Obviously if this be the old center of buoyancy, new center of buoyancy will be shifted somewhere here in this direction. Let B dash is the new center of buoyancy. So what it does now, if this be the G, now the force acting on this body is W vertically downward through G, and then we see that this AB. Now it is not very easy to say that always it will be a overturning moment or a destroying moment. In this case what do you see? That if I make a projection of the vertical through G like this, under this particular condition, this is which moment? Restoring moment. Very good. So under this case it is a restoring moment. That means it is angularly stable. But can we tell always if B shifts in this direction, just common sense you tell, always there will be restoring moment? No. If this B dash comes here, that means if I draw the vertical projection or a vertical line from the center of gravity, and if B cannot cross this vertical line towards this direction of heel, then it cannot create a restoring moment. So long it is here, so this force will always create a overturning moment. That means whether there will be a restoring moment or an overturning moment is not conclusively decided by the position of G above B, but the shifting of B with respect to G. If the shifting of B takes place like this, that it crosses this vertical line in that direction, then it creates a restoring moment. Otherwise it creates a overturning moment. So this is the condition. This is better stated analytically by this fact that if we make a vertical projection from the new center of buoyancy, make a vertical line, extended vertical line, and let it intersect with the old vertical line containing the center of gravity and the old center of buoyancy at a point M, and this point M is known as meta center. This is very important concept, meta center. And usually for a small angular heel, if we do not consider a very big angular heel, that means a small perturbation with small angular heel in either direction. So you can see if you give a tilt in that direction, the same condition will be there. That means B either create a overturning or a restoring couple depending upon its relative displacement with respect to G. Now this M meta center is usually for a small angular heel is a geometrical criteria. It depends upon the dimension of the body and this geometrical shape. So it becomes a geometrical criteria, meta center. Now we just see that the way we appreciated that if B crosses this vertical line in the direction of the heel, then it will give a restoring moment, otherwise a overturning moment, can be told with respect to this very important point meta center, that if meta center is above the center of gravity, in this case it is that, then the body is under stable equilibrium. And if the meta center is below, that means in this case, if this is the shift, then meta center, then the vertical line will always intersect at a point, at the same point known as M, which is below G. That means when meta center is below G, then we can tell that the body is not in stable equilibrium, and the height Gm, that means the height from the center of gravity to the meta center, if it is below, this is the height, this is known as the, along this old vertical line or the line of symmetry, you can tell is known as the metacentric. That means Gm, this distance is known as the metacentric height, which can be also written as Gm is equal to Bm minus Bg. If you write like that, when meta center is below center of gravity, then Gm is negative. That means we can tell Gm is greater than 0, Gm less than 0, and Gm is equal to 0. Three cases. When Gm is greater than 0, meta center is above the center of gravity. By this formula we define as analytically that it is greater than 0, m is above g and the body is in stable equilibrium. When gm less than 0 means m is below g, so we define it at bm minus bg, so that gm is less than 0, then the body is unstable equilibrium, that the couple created because of the tilt by the weight and the buoyancy force is an overturning one, that is the unstable equilibrium. And when metacentric height coincides with the g, that means the b is displaced in such a way that the vertical line through b just intersects g, that means again in that displaced position fb and w become collinear. If it satisfies that, that means gm is 0, that means bm is equal to bg, which means the vertical projection from the new center of buoyancy intersects this point, then this is the neutral equilibrium. So therefore, it is not conclusive only from g above b, which was there for submerged body, it will be under unstable equilibrium for a floating body. The key point is that in this case, since the center of buoyancy moves towards the direction of the heel, it gives a advantageous condition. That means when the center of buoyancy moves towards the direction of the heel, it gives an advantageous condition even if it is a top heavy, that means the center of gravity is above the center of buoyancy till it is in equilibrium, stable equilibrium, provided the meta center is above g. That means the buoyancy is shifted in such a way that it crosses the vertical line from the center of gravity, so that it creates a restoring couple to allow the body to come back to its original position. Well, so this concept is now clear. Now with this concept in metacentric height, I will derive now a very important relation. What exactly is required for designing a floating bodies in practice? For example, a ship, that the metacentric height should be made positive, so that for any angular rotation or angular disturbance of the ship about any horizontal axis, ship is stable. Now this metacentric height I have told, or the metacenter, position of metacenter is a function of the geometrical shape of the ship or geometrical shape of the floating bodies. So if we know beforehand by calculate this metacentric height from a functional relationship of the metacentric height with the geometrical dimension of the body, accordingly we can design the ship that make the geometrical dimension so that the metacentric height is always positive and it should be as big as, that means mg should be high at high positive value, so that stability is ensured even under a greater perturbation. So for that we try to seek, or we seek a functional relationship between the metacentric height or the position of the metacenter in terms of the geometry of the body. Let us do that. Well, again we make the same thing, that this is the body, we have the floating bodies, body like this, make the floating body like this, that is the cross section of a ship, rather you take a cross section of a ship, this is the plane area. Now after the heel, let us, could have been better with different, well, so this is after heel, is the displaced position. Now let us see, first we consider a simple case always, that g is above b, that is not the simple case is that g remains unchanged. Let us consider this is g, but the old b, obviously when you give a tilt in this direction, what will happen? Old b will be shifted here, b dash. So the weight acting through this, and this is acting b, fb, and this is w. Now if we trace this old line for the plane of flotation, we can write, or we can draw like this. Let this is the point O, point of intersection of the original plane of flotation. Well, this is the original plane of flotation and the new plane of flotation, and let they intersect along their centroidal axis. We assume that. Now one thing is true, so long W is equal to FB, well, W is equal to FB, that means this is the W. This always we consider equilibrium. only we are considering the stability, that is angular stability. Then the buoyancy force W is unique, so buoyancy force is unique. So therefore, by the principle of Archimedes, the immersed volume should remain same, whether it is given a tilt or not, which means the volume which has come up, that means this hatched portion, must be equal to the volume at this hatched portion which has gone inside the liquid. This is the key point, nothing else. So this volume is equal to this volume of liquid. So this is all right. Now if we simply define the center of buoyancy with respect to any frame of reference, now we will have to do, let us consider this as O in this original figure. We consider the axis like X and this is as Z, vertically downward Z, and the horizontal axis is on the plane of flotation, and take Y the perpendicular to the plane. That means if we see this cross section like this, a cross section like this, a cross section, just an arbitrary cross section like this, so Y will be along this direction. That means if we define O somewhere here, this is the OY. That means this is in this perpendicular. X, Y and vertically downward is the Z. I think it is all right. Now if we define the center of buoyancy X coordinate as XB, which is definitely 0 under this condition, because this is the Z axis, that means distance from the Z axis. So XB, then we can write that V, the immersed volume, into XB is nothing but, if we take here a prismatic body of the fluid or the volume immersed whose cross sectional area is dA, and Z is the coordinate, that means this is the height of this prismatic element, that means, or Z coordinate of this point, whatever you can tell, that this becomes equal to Z into dA into X, sorry, Z into dA into X, rather we can write Z X dA. All right. Now you see that here what happens, that is the Z dA is the volume and moment of the volume, that is the center of buoyancy. Now this case it is 0. If we define center of buoyancy on this line, this case it is 0. Now this case what we can do, we can, now the axes are defined from this, so therefore Z and X will be like that, but here if we take, now this is immersed here, so if we take a prismatic volume like this, what is its height? So this dA we can show it here, this is the dA. This is typically the elemental area in this plan, that means this view. Now where, here if we take the same prismatic element dA, here the height is equal to Z, that means Z is this one with respect to this coordinate axis X, and this is Z, plus this extra amount which has become immersed in the fluid. So if this is the X, that means the X coordinate of this prismatic element from the coordinate axis origin, then this will be X tan theta, where theta is the angle of heel, that means this is theta, if we make this as theta, or the vertical through this O with the old vertical theta, because angle between two lines is equal to angle between their perpendicular. So theta is the angular heel, that means theta is the angle between the old plane of flotation and the new plane of flotation, or between the old vertical line and the new vertical line. So this is the theta. So therefore if this is X and this is theta, so this extra part is what? X tan theta. That means now we can write Vxb dash. If xb dash is the, this is the b dash, that is the, this is the b dash, that is the x coordinate of the new center of buoyancy. What we can write? We can write that is equal to Z plus X tan theta into dA. Simply we subtract this upper one from this one, we get V into xb dash minus xb is equal to, tan theta is constant because angular heel is constant throughout the body. So therefore we can take tan theta into what? X square dA. Sorry, x, yes, one x is missing for the moment. So z x plus tan theta dA is the volume, elementary volume and moment for moment x. So simply x square tan theta. All right. So this is equal to, now you see we can write, this is okay. Now we can write, well, now what we can write? We can write that V into x b dash minus x b is equal to what? Tan theta into x square d. Now x b dash minus x b for small angle of theta, if you make a projection from this to this axis, this is the axis z. So for small angle of theta, this can be written as b, this is b, and if this vertical line intersects at a point, let this is m, so this b dash can be written as bm tan theta, bm tan theta. For small angle, we can write this, if we make an perpendicular from b dash on this old vertical line, which is the z axis rather, we can tell for small angle this perpendicular does not make any change from b to this point of projection. So we can take simply from this right angle triangle, this vertical line meets at m, so this is bm tan theta. Okay, so we can write bm tan theta for small angle tan theta, because this projection may not coincide with b. That's why the small angle concept we can write, this is almost equal to bm tan theta. So tan theta cancels. Well, so we get what? Bm, sorry, this is bm tan theta, so b is there. So bm is equal to x squared dA divided by v. Now what is this x squared dA? What is this x squared dA? If we just see here, x squared dA, now we see to this figure, that means x is the distance of any elemental area here from this y axis. That means this x squared dA, which is there in the numerator of this expression of bm, represents what? The moment of, second moment of area of the plane of flotation. This is the plane of flotation. That means I see here as a section from here. If I take a section from here and look from top, that is the sectional plan we see. That is the plane of flotation. So x squared dA is the second moment of area of the plane of flotation about the centroidal axis. About the centroidal axis, which is perpendicular to the plane of rotation. This is the plane of rotation. That means this is the second moment of area. Be very careful. This one, second moment of area of the plane of flotation about this OY, which means physically about the centroidal axis, that means this axis here, which is perpendicular to the plane of flotation. Plane of flotation is the xz plane. So y axis is perpendicular to that. Or you can tell that it is the centroidal axis of rotation about which the rotation is taking place. So if you can understand this nomenclature, x squared dA as we defined as I, simply I, we make IY. Again y makes a confusion that you will have to take this as the y axis. So simply I tell I, so that I can write Bm is equal to, this is a very important formula, I by V. So nomenclature is like this. Bm means, what is Bm? It is the distance from the center of buoyancy to the metacenter along the old line, vertical line where center of buoyancy and center of gravity was acting. So along this is the Bm, where the Gm is the metacentric height. Bm, therefore this is the definition, and usually it is told as metacentric radius. Not very common, but you will see in my book I have written that not all the books they tell, because it is not a very common terminology as Gm metacentric height, but Bm you can tell metacentric radius, distance between the buoyancy and the metacenter along the old vertical line. So this is Bm, which is equal to I by V. So you will have to recognize the nomenclature like this. V is the immersed volume, that is the volume of the solid which is immersed in the fluid, displaced volume, and I is the moment of inertia of the plane of flotation, moment of inertia of the plane of flotation about the centroidal axis which is perpendicular to the plane of rotation or the axis of the rotation. That means if you take a simply parallelepiped, the plane of flotation is the horizontal projection of the area, that horizontal, this plane, and this perpendicular axis is the centroidal axis perpendicular to the plane of rotation. So the nomenclature of I should be very important. Now you see, in case of a ship, if you see the structure of a ship, now the ship, if you see a ship, now this is the, now if you see this ship, this is the elevation. If you see its plan, now the structure of the ship is such that, like this, there may be two axes, vertical axis, a horizontal axis, let x and y. Now movement of the ship about, now you see one thing, that the movement of the ship about this y axis, that means in this direction, is known as rolling, transverse axis. And movement of the ship about this axis, that means about the longitudinal axis, that means in this direction, is known as pitching. Now when the angular stability for rolling, that means about this y axis, pitching is about the transverse axis, that means it moves like this, and rolling is about its longitudinal axis. When rolling angular stability with rolling is considered, then the I corresponds to the second moment of area about OI. Similarly, when the angular stability with respect to pitching is considered, that means it is its angular movement about x axis, then the moment of inertia about the axis x, OX is considered. Okay, let this is OX. Now you see, from the typical geometry of the ship, the second moment of area about y axis is much lower than the second moment of area about x axis, because the longitudinal dimension is more. So therefore I is lower in case of rolling as compared to that in case of pitching. Clear? So therefore Bm is I by V. So therefore in case of rolling, Bm is small, because I is small. Rolling is about OY axis. So about OY, the inertia, moment of inertia is small. So therefore stability with respect to rolling is more important than the stability with respect to pitching. Ship is almost stable with respect to its rotational motion or with respect to pitching about x axis, because the moment of inertia of any element about the x axis is much higher. So rolling, for rolling, the stability is more important. That means we will have to see the angular stability point of view, that it is the moment of inertia of the plane of flotation about an axis makes it more vulnerable for its angular stability in a particular direction. Well, thank you.